Hello physics students. Welcome to the Energy Level Lab. Now at this point, you should have already printed out all 4 pages of the document included in the Google Classroom stream because you'll need all of them for your data, your calculations, and for answering the questions at the end of the lab. Now, what we're going to do is a very exciting lab because what we're going to do in the lab is we're going to verify that incredible theory that I talked about a couple videos ago. And that's that particles, what we thought of as particles, like electrons, protons, and neutrons, are actually not particles. They're waves most of the time, these imaginary waves that move through space and interact with other imaginary waves. And what that means for an atom is that the energy that it can absorb and the energy that it releases is quantized. In other words, it comes in fixed steps. So the reason for that is because if you take hydrogen and you have a proton in the middle, then if an electron orbits as a wave, then the only possibilities are that one wavelength fits or wraps around in the orbit, or 2 wavelengths or 3 wavelengths, but not 1.5 or 1.7 wavelengths. It's got to be either 1, 2, or 3, so on and so forth. And what that means is that the orbits come in fixed steps and the energies rising or falling come in fixed steps. And the fancy word for that is quantized. It's like a staircase of energy. So to verify that, what I'm going to do is use the spectrum tubes that I showed you earlier when I first talked about the Bohr model and one of these spectrometers. And what we do is we shine the light, as I mentioned, from a source like this. This is a glass tube with hydrogen in it. I pass electricity through it and energize it. And then that light that comes, so I'm energizing it, giving the atoms energy so that the electron goes to a higher orbit. And then when it falls back down, it releases light in fixed steps. And that light then goes into the spectrometer in this little hole. And then when you view it, what happens is there's a diffraction grating here. So the light still retains wave properties. It does still diffract through this end. And then when it diffracts, it kind of spreads out the colors, and we can measure the exact wavelengths of the particular light that's released. So that's what we're going to do. We're going to set this up. We're going to have the light come through the spectrometer. And then what I'm going to do is I'm going to have this camera capture the view so that you could see it at home, what we see in this spectrometer. But first I have to turn this light on. Well, actually, before I turn it on, I don't want it to get too hot. I first have to get rid of the lights in this room. So I'm going to pull the shade down over here. And I'm going to go run over and turn out the lights. I'll pull this shade down behind the camera too, darken it a little bit more. And then so I can see the scale in this side of the spectrometer, I'm going to need a little backlight. So I'm going to turn this little light bulb here on. So it provides a little light for the spectrometer. And then I'll turn this on. And as you can see, let's see, can't see it too well, but you should see like a purplish glow over here coming out, going into the spectrometer, into the camera. So now what I'm going to do is switch through editing to show you what this camera is seeing. So let's take a look. And here's the hydrogen spectrum. Just a reminder that white light would create a full rainbow going across that whole scale, but the hydrogen gas is stimulated by electric current, causing the electrons in the orbits to rise to a higher level. That doesn't produce the light. What produces the light is the electrons falling back down into a lower level, and then they release only those colors of light. You should be able to see 3 distinct bands. All the way on the left of the screen, you could see a red band, and then in the middle, or a little to the right of the middle, you'll see like a bluish green band. and then all the way to the right, a really faint purple or violet line. We need to get the wavelengths of all three of those lines. So you see the scale on the bottom. It starts all the way on the right at 400 and then goes all the way to the left at 700. So it's backwards essentially. It runs from right to left instead of left to right. So the first one we can read is the purple or violet line. Starting at 400 and counting upward, we can get its wavelength. Now, each of those tiny spaces is worth 5 nanometers. Every second one is 10 nanometers. So I'm counting over. I can see 410, 420, 430. It's a little bit beyond 430, somewhere between 430 and 435. Maybe I'll say 433, okay? So that's the first wavelength, 433 nanometers. I'm going to go now and get the wavelength of the green line. So the little line to the left, or the bigger line to the left of the violet, is 450. Then I go 460, 470, 480. Looks like between 480 and 490, maybe like 486 nanometers is the green line. Okay, so, and then now we need the red line wavelength. So let's start with the 600, the big bright 600 at the bottom of the screen. And then if we go to the midpoint between 6 and 700, we get, actually maybe I shouldn't be lazy, I'll count over. So 600, 610, 620, 630, 640, I lost my place. Let's try again. 610, 620, 630, 640. Looks like a little bit beyond 650, maybe like 652 nanometers. So I'll write that down. Okay, so now that I have all my wavelengths, let's switch to the desk view. I'll guide you through the calculations and the analysis. As you can see right here, I copied the 3 wavelengths of the 3 lines we saw in the spectrometer. I didn't have to write units after each number because I have units of nanometers at the top of the table here, so it applies to all the numbers below it. So, of course, you're going to get your own values as always. So what I want you to do now is go into the Google Classroom stream, open the document that has all the data, find the 3 wavelengths assigned to you, and copy them in your data table. So go ahead and do that now. All right, well, we want to do an energy analysis now and see how this relates to the hydrogen spectrum, or I should say energy level diagram. So we have to calculate the energy of each of these lines. And that's what we're going to do right here. So what I want you to do is first go and find the formula for the energy of a photon. And remember, we do not have frequency, we have wavelength. So find the formula that has wavelength in it. Then, as always, we need 3 steps. We write the formula. Next, we're going to plug in the numbers and the units. And when we plug in the wavelength, you have to realize that this is not meters, it's nanometers. So what you have to do is plug in the wavelength in meters by getting rid of that nano symbol. So, for example, for my number, it's 652, and then nano means something. So I'm going to put times 10 to the some power here. I'll leave that for you to figure out what goes into the exponent, and then, of course, the meters. So you have to plug in your wavelength like this. And then once you plug that in, you punch on a calculator, and you get the energy, and the energy in some number of units. Actually, it says in joules, so I guess I could tell you that. So go ahead and make that calculation now, the energy in joules of the red line. Okay, and just before we move on, if you didn't get a power times 10 to the minus 19th here, then you did something wrong with your conversions. Go back and fix that before you go on. Now we're going to repeat for these 2 other lines in these boxes. the blue-green line. So we're going to, again, start with a formula, every time starting with a formula. I know we're repeating, but you still need the formula. Plug in and get your answer. Plug in the numbers and then the answer. And then for the violet line, you're going to do the same thing. So go ahead and calculate these energies in joules. Now, again, if you don't get times 10 to the minus 19th for both of your powers, then you did something wrong. You're going to have to go back and try and figure out where your error is. So go ahead and do that now. Okay, so the problem with these numbers is that the hydrogen energy level diagram in our reference table does not have the energies in joules. All these energies are in electron volts. So what we're going to have to do is convert our joule values to electron volts. So that's what these spaces are over here. So what you can do is you could start with your energy in joules. Remember, there's some number here that's just what's here. And then you're going to multiply by a fraction. Okay, so, and then all you need are two steps: setting up your conversion with dimensional analysis, and then your answer in electron volts. So go ahead and do this two-line calculation for the red line. Go ahead and do that now. Okay, so I'll just tell you again, a check. If you got some kind of power here, then you did something wrong. Like it should be, I'll make up a number, 3.85 or something like that. It should be some number less than 10 with no power times 10 to the something or other. If you have some power, again, go back, check. It should just be a number between 0 and 10. All right, we're going to then repeat that conversion for the other two lines. Again, just two-line calculation here, not the standard 3. And again, your two answers should be less than 10. So go ahead and make those conversions now. All right, so these are the energies in electron volts of those three lines that we observed in the spectrometer. What we're going to do is now go on to the next part where we analyze and see how that pertains to the hydrogen atom. So basically this whole paragraph says that these lines are created. Remember, they're created when an electron drops down in the hydrogen atom. The paragraph tells us that it drops and ends in the n equals 2 state. There are electrons that drop all the way down to n equals 1, the ground state. The problem is, well, I don't want to tell you the answer because that's one of the questions later in the lab. The point is, we didn't see them in the spectrometer. All the ones that we saw stopped and fell from some higher level down and ended into the n equals 2 level. So that's why the final energy is negative 3.4, as we could see right on the reference table. Now what you're going to do is figure out, well, where did these electrons come from when they produced the line? Which of these states? So what you have to do, you have to take the numbers from the previous page, like the red line. I shouldn't have picked the numbers so big. Let's say it's 2.9 or something EVs. The question is, how do you figure out what the initial energy is, where it started? If it fell down and landed in negative 3.4 and it fell a total of 2.9 EVs, or whatever EVs you had calculated here, what do you do with these two numbers to figure out that initial energy? Think about it, and then do that calculation and put the answer over here. I don't know, I'll put negative 1.7 or something, I don't know. Whatever your answer is, it belongs there. So go ahead, I made up a number again, right? But you're going to go ahead and calculate with these two numbers go ahead and calculate the initial energy of where the red line was created. Go ahead and do that now. Next, you're going to do that for all the other lines actually, you know what? Let's finish with the red line. Now, so we know that the electron started in this state and it dropped to this state. So what you have to do is now find the initial energy level that the electron began in. So mine was negative 1.7. Again, I'm not saying that's correct, but what you do is you go back to this energy level diagram and you look for the closest one. I guess for me, the closest thing to negative 1.7 is negative 1.51, which is the n equals 3 state. So I would fill in n equals 3 in here for the initial state. Now, of course, the electron, as we learned, should be in only exact energy levels. So technically, at negative 1.7, there is no energy level there. But again, this is an experiment with error. So you may not hit an exact energy level here on the reference table. Just find the closest one because, again, of measurement error. In theory, the numbers should be exact. They're not because it's an experiment. So go ahead, figure out what integer, 3, 4, 5, 6, what number you put here. Go ahead and do that now. We're going to repeat that same analysis for the other two lines. So for example, the blue line was some number of EVs. I'll make up a number. Maybe it's 1.8 or something. I don't know, right? So you have a calculation here. Now figure out where did it start if it fell that far and landed in negative 3.4. Go ahead and make that calculation and then the same calculation for the violet line. Go ahead and fill these energies in now. And then go on the reference table and see which energy the electron began in to produce that line. Find the closest one and then find the number that corresponds to and fill it in here and here. Go ahead and do that now. All right, so we've finished with the hydrogen atom. We figured out where the electron started and where it fell to, where it started, where it fell to, started, fell to produce these three lines that we saw in the spectrometer. So that was the hydrogen spectrum. Now, as you know from the homework assignments, when we learned about the Bohr model of the atom, the other atom or element, I should say, that we study in the Regents physics curriculum for energy level diagrams is the Mercury atom. So that's what part 2 of the lab will be. I'm going to switch out this hydrogen tube with a tube that contains mercury in it. So here's the tube that has mercury in it, and hopefully this isn't too hot, not too bad. And you'll see that this is a different color. It's like a bluish purple color. So that creates an entirely different spectrum because the electrons in the mercury have different set of orbits, as I talked about during the Bohr model video. So we're going to now take a look at the spectrum this camera is recording, and then we're going to analyze it to see that what we're seeing here matches up with the steps in the mercury atom. So let's have a look. Okay, here is the mercury spectrum. I could see I need to adjust it a little bit, so let me make some adjustments there. Okay, there we see more lines coming up. Again, a reminder, this is because the electrons in the mercury atom were bombarded by electric current and bumped up to a higher orbit. That didn't release light. What released these lights that you see is when the electrons started falling back down, or when they fall back down to their lower orbits that they originally started in. So we are going to record the wavelengths of each of these lines. The first one, we'll start on the right, and I think it's easier that way, with the violet line. And I see the violet line is not visible. Let me try and adjust this a little bit. It's always a little hard to see the violet line. Oh, there it is. Well, it's not really showing up. Maybe that's it on the right, the very right. You could see a very faint line, and so we're going to record that wavelength. And so that, starting at 400, I count up 410, looks like about 415 nanometers for the violet line. Next, we're going to go over to the next one to the left, the real bright blue line. And that's starting at 400. I'll count up 410, 420, 430. Looks like maybe 434 nanometers. And then what we want next is the bright green line. And so you see there are a few green lines, but the brightest one right in the middle, if we start at 500 and count over, 500, 510, 520, 530, 540, looks like, I would say about 543 nanometers. Yeah, 543 nanometers. And then the last one that we want to get is the red line. So I see a few red lines. Let's go with just the brightest one. Starting at 600, the nice bright 600 near the middle of the screen, I'm going to count over from there, 610, 620, 630, 640, 650. So that looks pretty much on the dot, 650 nanometers. So there, I have my wavelengths. Let's now go and do some calculating and some analysis. So I've copied all the wavelengths that I saw in the spectrometer or measured in the spectrometer here. Notice I didn't put any units after every number because I have units in the top of the table, so it applies to all these numbers. But you're going to have your own numbers, as always. So what I want you to do is open the document again in the Google Stream that has all the data. Find the data assigned for you, the wavelengths for all the color lines, and copy them in your data table. So go ahead and do that now. All right, so next what we're going to do is we're going to figure out the transitions involved in this experiment, but we're going to focus in on the green line this time, not all of them like we did with the hydrogen analysis. So we're going to start here, and you see here in this box it says, calculate the energy of the green line in joules here. So we do the same thing we did on the previous page. We start with a formula, the one that has wavelength in it, not the one that has frequency, because that's what we have. You're going to plug in all your numbers, but when you do, you're going to remember that this is not meters. The wavelength is not 543 meters, it's 543 nanometers. So you have to get rid of that nano with the power 543 or whatever your number is times 10 to the something power. Look that up on the reference table if you don't know, and plug that in appropriately to the formula, and then get your answer here in joules. And again, the hint, if you don't get times 10 to the minus 19th, you did something wrong. So go back and try and figure out what you did wrong. And then that's your energy in joules. Go ahead and make that calculation now. The next thing you have to do is convert that to electron volts. Once again, all these energies on the reference table are not in joules. They're all in electron volts, so we need to convert so we could compare to our reference table. So as before, you start with your joules and you multiply by a fraction, like the chemistry dimensional analysis that you did last year. And then just 2 steps, the answer here will be in EVs. Once again, as before, this number should be between 0 and 10. If you have some kind of power, 10 to the minus something or other, or 10 to the positive something, you did something wrong. It should just be a number between 0 and 10. Go ahead and do that calculation now. All right, now what we want to do is figure out what two states the electron jumped between to produce that green line. Did it go from the I down to the G, or did it go from H down to C? That's what we want to find out. So how do we do that? What we do is we imagine for a moment that it fell and landed in the A state at the bottom at this final energy. And it would have fallen this many EVs. I'll make up a number. Maybe it's, I don't know, 0.7 or 1.7 or something like that. Again, I just made up a number. So what you're going to do is figure out with this number and this number where it would have started if it fell down 1.7 and landed at the bottom 10.38. Where did it start? You do something mathematically with these numbers, and then you fill in the answer there. Go ahead and make that calculation now. All right, well, it turns out that that is not the transition it made, but you will see that later. What you want to do is find the actual transition. So you're going to now assume it landed and fell down into the B state from one of these higher energies and fell down and landed here in this energy. So you need to take this number and repeat that same operation you just did and calculate a new hypothetical and initial energy. Go ahead and do that now. And then repeat with all these hypothetical final energies. That same math operation with these numbers and this number, and you should have numbers all throughout this table here filling in this entire column. So go ahead and repeat that calculation on all of these numbers, fill in that column. Go ahead and do that now. All right, now the challenge is to figure out the actual transition. So let's suppose that somewhere here we got negative 1.56. Okay? You won't, because I'm just making up numbers. And all these are all different negative numbers. So what you do is you go to the reference table and you see, actually let's do, maybe I'll do this, not this one. Let's do negative 2.49, something like that, okay? And now you look at all these numbers here and you see if any of them match in the Mercury atom's energy level diagram. You see 2.48 and 2.49 negative, both are pretty close. And so for me, that would be the match. This is the initial energy because none of these here will match any other as well as this one. There'll only be one number here that's the closest match to these energy levels. So find your number. Go ahead and find it and circle it. What's number closest matches one of these over here? Go ahead and do that now. All right, so that would mean that my electron started at this state, which is G, and fell down to this state, which is E. So it fell from G to E to produce my green line. And so what I would do, what I would answer here is identify the initial and final. I would say the initial was, as I said, the G state. And the final was the, what did I say, the E state. Again, yours will be different because I made up numbers, but that's how you do it. Go ahead and write the initial and final states. What they are is letters in this box. Go ahead and do that now. Okay, moving on. So the next thing we're going to do is we're going to do a calculation. Here, we will analyze Mercury atom's violet line. Suppose an electron produces this line by transitioning from F to the B state. Using your reference table, determine the energy released by the electron in electron volts. So what we do is we look up the F and the B state energies on the reference table. We get those numbers, and then we're going to calculate the energy of the violet line from those two numbers. We're going to write out a formula. We're going to plug in the numbers here, and then we're going to have some number answer here for electron volts. 3 steps with the 2 numbers from the reference table. Go ahead and make that calculation now. Well, in order to figure out the wavelength, we need the energy not in electron volts but in joules. So what you have to do is you have to make a conversion like we've done already several times in this lab. You're going to start with the electron volts from here, multiply by a fraction, and then have an answer in joules. Go ahead and make that conversion now. Once we have this energy in joules, step 8 says calculate the wavelength of this photon. That's what it says up here. So we're going to now look for a formula with energy and wavelength in it. And then we're going to plug in our numbers, and then we're going to get a wavelength. And you should get something times 10 to the minus 7th meters. If you don't get times 10 to the minus 7, you made a mistake somewhere, and you're going to have to find it. But go ahead and calculate the wavelength now. And now we have to calculate the percent error. So again, this is the theoretical value. It's the value as determined by formulas off the reference table and data on the reference table. The experimental value, the value we measured in our experiment, is right here. Now, at first, you might look at this number 415 and think that it's way off because this number that you just calculated is 400, something like maybe like 4.3 or something. I forget what it is, but it's this number of meters, but this is nanometers. So when you add the proper power here that you have to find on the reference table, you'll see that when you calculate the percent error with these two numbers, you're going to get something pretty small, like maybe 1 or 2% or something like that. So that, of course, is calculated like this: absolute value, the theoretical value, minus the experimental. This is the experimental, all over the theoretical, times 100%. So if you just put these numbers in on your calculator with the powers as is, or you could convert them to have the same number of powers, either way, you calculate the percent error and you should get, like I said, a pretty small value. So go ahead and calculate your percent error now. All right, so time to move on to the last page. The last page is just questions. So what you're going to do in number 1 is you're going to go back to the hydrogen atom. In the case of the hydrogen atom, you only observe photons released from transitions 2 n equals 2. Suppose the electron transition from 2 to 1. Calculate the energy of the photon in EVs using your reference table. So again, here are the energies in your reference table. Look the energy up for 2 and 1, those two states, and then calculate the energy of the photon. Remember, you're going to need a formula first, then you're going to need to plug in numbers in, and you're going to get an answer. So go ahead and make that calculation now. Now, you're going to have to convert this to joules. So we've done this a couple times already in the lab. You're going to take this number, and you're going to make a conversion. This, you only need 2 steps here, and now you'll get your photon in energy in joules. So go ahead and make that calculation now. Next, from this value, we can calculate the frequency of the photon. So that's what we do here. You look up for a formula that has energy and frequency in it, write out the formula, plug in the numbers into the formula, and then when you're all done, get the frequency. So go ahead and calculate the frequency now. All right, next question. Use the electromagnetic spectrum in your reference table to identify this type of radiation. Explain why you did not see any of this radiation in your spectrometer. So what do I mean By that, well, remember in the waves topic, we learned about this electromagnetic spectrum. You're going to use this frequency here and look up in the spectrum what kind of radiation that is. Like, for example, maybe you think it's a microwave. You would write microwave, the word microwave. It's not a microwave, by the way, but I'm just writing that there as an example. So you're going to put a word here of the type of wave it is. So go ahead and identify that radiation of the photon and write that there now. And then the last part, explain why you did not see any of this radiation in your spectrometer. So you're going to write out some sentences why we didn't see a line for this kind of radiation in the spectrometer, a couple sentences, and then that's the explanation there. So go ahead and write the explanation now. So that was the Energy Level Lab. I hope you are as fascinated and as impressed as I was with the fact that we were able to take this power supply, glass tube, some elemental gas, some plastic, and a camera, and we were able to verify this incredible idea, this mind-blowing idea that particles that make up everything in our world are actually imaginary waves that move around, and in this case, they wrap around the nucleus of an atom, that wave, and that makes fixed energies in the atom. So I hope you enjoyed. I'll see you in the next physics video.